Hello and welcome. Today, we'll be solving the problem titled Insert into a Sorted Circular Linked List. This is a fascinating problem that challenges our understanding of linked lists and edge case handling. In this session, we'll explore efficient ways to solve it, and by the end, you'll have a clear strategy for tackling similar problems. Let's dive in. In this problem, we are tasked with inserting a value into a sorted circular linked list. A sorted circular linked list is a data structure where the nodes are arranged in non-decreasing order, and the last node connects back to the first node, forming a complete loop. The list is given to us via a reference to its smallest element, called the head node. If there are multiple nodes with the same value, we can choose to insert the new value after any of them. Our goal is to write a function that takes two inputs, the head of the circular linked list and the value to be inserted, called insertVal. This function should insert the value while maintaining the sorted order and return the original head of the updated list. If the list is empty, meaning the head is null, we will create a new single-node circular list with the given value and return this new node as the result. The function we write should return the updated head node of the circular linked list. Let's consider an example to understand this better. Suppose the input head is 3, 4, 1, and the value to insert is 2. Initially, the list is circular, 3 points to 4, 4 points to 1, and 1 points back to 3. Our task is to insert 2 while maintaining the sorted order. The correct position for 2 is between 1 and 3. After the insertion, the updated list will be 3, 4, 1, 2, or 2 points back to 3, preserving the circular structure. Another example illustrates the case where the list is empty, with an input head of and insertVal 1. Here, since the list is initially empty, we create a new circular list with one node containing the value 1. This new list consists of a single node where the next pointer of the node points to itself, forming a circular structure. Let's now examine the case of a single node list. For example, if the input head contains 1 and the insertVal is 0, the initial list has only one node, 1 points to itself. To maintain the sorted order, the value 0 is inserted, resulting in the updated list 1, 0. In this updated list, 1 points to 0, and 0 points back to 1. This ensures the circular property is preserved. These examples illustrate how the function must handle various scenarios, including inserting into an empty list, a single-node list, or a multi-node circular list while ensuring the list remains sorted and circular after the operation. To solve this problem effectively, we must keep in mind several constraints and edge cases. First, the number of nodes in the list can range from 0 to 10,000, and the values of the nodes, as well as the insertVal, are within the range of -1 million to 1 million. Some important edge cases include handling an empty list by creating a new node, managing single-node lists where the new value could be smaller or larger than the existing value, and dealing with duplicate values where the new value can be inserted after any instance of the same value. Additionally, we must account for cases where the value to insert is smaller than the smallest value or larger than the largest value, requiring us to wrap around the circular structure. If all nodes in the list have the same value, the new node can be inserted anywhere. Finally, since the list can have up to 10,000 nodes, our solution must be efficient to handle large inputs within these constraints. To solve the problem of inserting a value into a sorted circular linked list, we first considered the brute force approach. The intuition behind this method is fairly straightforward. Traverse the entire list until you identify the correct position to insert the new value, ensuring the list remains sorted. The process begins by starting from the given node and iterating through the list. At each step, you check whether the current node's value is less than or equal to the value being inserted, and the next node's value is greater. Once this condition is met, you insert the new value between these two nodes. Additionally, edge cases must be addressed, such as when the new value is smaller than all existing values or larger than all existing values. In these scenarios, the value is inserted at the appropriate position to preserve the circular structure. Although this approach is simple to implement, its complexity is O(n), since you may need to traverse the entire list in the worst case. This makes it less efficient, especially for larger lists, and is therefore not ideal for this problem. Next, we have the optimized approach, which is the method we ultimately chose. This approach leverages the sorted property of the list to reduce unnecessary traversals. Instead of scanning the list linearly, we focus on specific conditions the insertion point must satisfy. Starting at any node, we traverse the list while checking two key conditions. First, if the current node's value is less than or equal to the value being inserted, and the next node's value is greater than or equal to it, then we insert the new node between the current and next nodes. The second condition accounts for the circular nature of the list. If the current node's value is greater than the next node's value, which indicates the end of the sorted order, we insert the new value if it is smaller than the smallest value or larger than the largest value in the list. In the rare case that no suitable spot is found after traversing the entire list, we insert the value at the end and reconnect it to the head to maintain circularity. While this approach also has a worst-case complexity of O(n), it is more efficient overall because it uses the sorted property to streamline traversal and handles edge cases in a clean and structured way. We also considered a recursive variant of this approach, but it introduces additional overhead from function calls and risks stack overflow for very large lists, which makes it less practical. The optimized approach was chosen because it strikes the right balance between clarity and efficiency. It fully utilizes the sorted nature of the circular linked list, reducing unnecessary traversals and cleanly handling edge cases like inserting the smallest or largest value. A few key observations guided this decision. First, the circular property of the list allows for indefinite traversal, so it's important to implement explicit checks to prevent infinite loops. Second, the sorted structure of the list enables us to stop traversing early once the correct spot is identified, which improves efficiency. Finally, edge cases, such as inserting values outside the current range, can be handled directly without compromising the circular structure. When compared to the alternatives, the brute force approach is simpler but inefficient, while the recursive approach is elegant but introduces unnecessary complexity and risks. The optimized approach, being iterative, efficient, and robust, addresses all these concerns effectively. By choosing this strategy, we achieve a solution that is both practical and reliable, making it the ideal method to solve this problem. In this problem, we are working with a sorted circular linked list, which is a unique variation of a linked list where the last node loops back to the first node, forming a closed structure. Our goal is to insert a new value into this list while ensuring the list remains sorted after the insertion. To achieve this, we use a linear traversal approach that helps us identify the correct position for the new value and update the circular structure appropriately. The first step in this process is handling the edge case where the list is empty. If there are no nodes in the list, we create a new node with the given value and set its next pointer to point to itself. This ensures the circular property is preserved even when the list contains just one node. To begin the traversal, we initialize pointers to help us navigate the circular linked list. First, we create a pointer, current, and set it to the head of the list. We also initialize another pointer, next_node, to point to current.next. With these pointers in place, we can begin traversing the list to find the correct insertion point. The insertion point depends on three possible scenarios. The first scenario is when the new value fits between two consecutive nodes, meaning the condition current.val equals insertval equals next_node.val is true. The second scenario arises when we reach the end of the sorted list, where the largest value wraps around to the smallest. In this case, we check if current.val next_node.val and determine whether the new value should be inserted as the new smallest or largest element. Finally, if we traverse the entire list and come full circle back to the head without finding a suitable spot, it means all the nodes have the same value, or the new value can be inserted anywhere. In this case, we insert the new value after the current node. As we continue traversing the list, we keep updating the current and next_node pointers to progress through the nodes. Once the correct insertion point is identified, the next step is to insert the new node while preserving the circular structure of the list. To do this, we first create a new node with the given value. Then, we set the next pointer of the new node to point to next_node, effectively linking the new node to the subsequent node in the sequence. Finally, we update the current.next pointer to point to the new node, completing the insertion process. These pointer updates ensure that the new node is seamlessly integrated into the list while maintaining the circular property. There are several key insights to keep in mind when working with this algorithm. First, the circular structure of the list means that we can traverse infinitely without encountering a null pointer, but this also requires careful handling of the next pointers to avoid breaking the loop. Handling edge cases is also critical. For an empty list, the new node becomes the sole node and points to itself. When all nodes have the same value, the new value can be inserted anywhere. If the new value is the smallest or largest, it must be placed at the appropriate position. Regarding complexity, the traversal runs in O(n) time in the worst case, where n is the number of nodes in the list. This occurs if the correct position is at the end of the list. The circular linked list is particularly useful here because it allows constant time traversal from the last node back to the first. Using two pointers, current and next underscore node, ensures that we can efficiently identify the correct insertion point. To illustrate this process, let's walk through an example. Suppose we have a circular linked list with nodes 1-3-4- back to head, and we need to insert the value 2. First, we initialize current to point to the node with value 1 and next underscore node to point to the node with value 3. As we traverse, we check if the condition current.val equals 2 equals next underscore node.val is satisfied, which is true for 1 less than or equal to 2 equals 3. This indicates that the new value fits between these two nodes. To insert the value, we create a new node with the value 2, update current.next to point to this new node, and then set the new node's next pointer to point to next underscore node, which is the node with value 3. The resulting circular linked list is 1-2-3-4- back to head, preserving both the sorted order and the circular structure. Finally, let's consider a couple of optimizations and the overall complexity of the algorithm. One useful optimization is implementing an early exit during traversal. If the correct insertion point is found early, the traversal stops immediately, avoiding unnecessary iterations. Additionally, the algorithm is memory efficient since it operates in place, modifying the existing list without requiring additional data structures. As for complexity, the time complexity remains O(n) due to the traversal of the list, while the space complexity is O(1) because no extra memory is used other than the new node. These characteristics make the algorithm both efficient and practical for inserting values into a sorted circular linked list. Here, we define a node class to represent each node in our circular linked list. Each node has a value, val, and a reference to the next node, next, which is initially set to none. Then, we define the solution class and its insert method, which handles inserting a new value into the circular linked list. First, we create a new node with the given value, insert val. Now, we handle the edge case where the list is empty. If the head is none, it means there are no nodes in the list, so we make the new node point to itself, forming a circular structure, and return it as the new head. If the list is not empty, we initialize two pointers, previous, starting at the head, and cur, pointing to the next node. We then enter a while loop to find the correct position for the new node. The first case we check is whether the value to be inserted falls between two sorted nodes, meaning it lies between previous.val and cur.val. If so, we break out of the loop, as we've found the correct insertion point. Next, we handle the case where the insertion occurs at the boundary, such as around the smallest or largest values in the list. This happens when previous.val is greater than cur.val, indicating a wraparound point. Here, we check if insert val is either greater than or equal to previous.val or less than or equal to cur.val, and if so, we break to insert the node at this boundary. If neither condition is met during the current iteration, we move both pointers forward by setting previous to cur and cur to cur.next. However, there's one more edge case to consider. If we traverse the entire list without finding a suitable position, we simply break out of the loop, as this means the new node can be inserted anywhere. Once the correct position is identified, we insert the new node between previous and cur. This is done by updating previous.next to point to the new node and setting new_node.next to point to cur. Finally, we return the head of the circular linked list. This ensures that the list remains properly connected in circular while maintaining its sorted order. Here, we start by defining the node class, which represents each element in our circular linked list. Each node object has an integer value and a reference to the next node. There are two constructors provided, one to initialize the node with just a value, and another to initialize it with both a value and a reference to the next node. Next, in the solution class, we define the insert method, which takes the head of the circular linked list and the value to be inserted as arguments. First, we create a new node with the given value. Then, we handle the special case where the list is empty. If the head is null, it means the list has no elements, so we make the new node point to itself, forming a circular reference, and return it as the new head of the list. Finally, we initialize two pointers, previous and cur. Previous starts at the head, and cur points to the node after the head. These will help us traverse the list to find the correct position for insertion. Now, we enter a while loop to locate the appropriate place to insert the new node. The first condition checks if the insertion value lies between the values of the previous and cur nodes. If so, we've found the correct spot and break out of the loop. The second condition handles cases where the new value needs to be inserted at the boundary of the list. This happens when the list wraps around, meaning previous.val is greater than cur.val. If the insertion value is either greater than or equal to previous.val or smaller than or equal to cur.val, it belongs at this boundary, and we break the loop. If neither condition is satisfied, we continue traversing the list by moving previous to cur and cur to the next node. To prevent infinite loops, we include a check to break out if previous comes back to the head, meaning we've traversed the entire list without finding a position. In such a case, we can insert the node anywhere, as the list is circular. After determining the correct position, we insert the new node between previous and cur. We update previous.next to point to the new node and set the new node's next to point to cur. This ensures the circular nature of the list is maintained. Finally, we return the head of the updated list. This approach ensures that the insertion always respects the sorted order of the circular linked list, handling edge cases like empty lists or boundary insertions seamlessly. To begin, let's look at the case where the circular linked list is empty, meaning the head is none. In this scenario, we need to insert a new value, and since there are no existing nodes, we create a new node with the value 5. This new node's next pointer is set to point to itself, making it self-referential and forming a single-node circular linked list. The result is a circular structure where the value 5 points back to itself, completing the loop. This new node becomes the head of the list, and the insertion is complete. Now, let's consider the case where we need to insert a value into an existing non-empty circular linked list. The input list here is 3-4-1-3, and the value to insert is 2. First, we create a new node with the value 2. We initialize two pointers, previous pointing to the head node, which has a value of 3, and cur pointing to the next node, which has a value of 4. Next, we begin traversing the list. The first condition checks if the value to insert falls between the values of previous and cur. Since 2 is not between 3 and 4, we move to the next pair, previous becomes 4 and cur becomes 1. At this point, we detect the circular boundary because prev.val is greater than cur.val. Here, we check if the value to insert is either greater than or equal to prev.val or less than or equal to cur.val. The value 2 satisfies the latter condition, so we break out of the traversal loop. Finally, the new node is inserted between previous and cur by updating their next pointers. The resulting list is 3-4-2-1-3, maintaining the circular structure. Finally, let's examine the case where the value to insert is either the smallest or largest in the list, requiring insertion at the beginning or end of the circular sequence. The input list is 1-3-4-1, and the value to insert is 5. We start by creating a new node with the value 5 and initializing two pointers, previous pointing to the node with value 1 and cur pointing to the next node with value 3. As we traverse, the first condition checks if the value to insert falls between previous and cur. For the pair 1 and 3, this condition is false, so we move to the next pair, previous becomes 3 and cur becomes 4. Again, the condition is false, so we proceed to the next pair, previous becomes 4 and cur becomes 1. At this point, we detect the circular boundary because prev.val is greater than cur.val. Here, we check if the value to insert is either greater than or equal to prev.val or less than or equal to cur.val. The value 5 satisfies the condition of being greater than or equal to prev.val, so we break the loop. The new node is inserted between previous and cur, updating their next pointers. The final circular list is 1-3-4-5-1, with the value 5 correctly positioned at the end of the sequence. To analyze the time complexity of our solution, we start with the initial check. If the list is empty, we create a self-referential node, which is a straightforward operation taking constant time, or O1. For the general case, where the list is not empty, we need to traverse the circular linked list to find the correct insertion point. The traversal involves iterating through the list, and in the worst case, we may need to complete a full loop through all the nodes. This happens, for instance, when the node needs to be inserted at the very end of the list, just before wrapping back to the head, or when edge cases require examining every node to satisfy the insertion conditions. During this traversal, each iteration involves evaluating two constant time conditions, so the traversal itself has a time complexity of O(n) in the worst case, where n is the number of nodes in the list. Once the correct position for insertion is identified, the next step is to insert the new node. This involves two pointer updates. We adjust the next pointer of the previous node to point to the new node, and then set the next pointer of the new node to point to the current node. Both of these updates are constant time operations, making the insertion itself an O(1) operation. When we combine the traversal and insertion steps, the overall time complexity depends on the specific scenario. In the best case scenario, such as when inserting into a single node list, the operation is O(1). However, in the average or worst case scenarios, where we need to traverse the entire list to find the insertion point, the time complexity becomes O(n). Now, let's consider the space complexity of the algorithm. First, we create one new node for each insertion. Since each node only contains two fields, val and next, both of which require constant space, the memory usage for the new node is O(1). Additionally, during the traversal, we use two pointer variables, previous and cur, to navigate through the list. These pointers are independent of the size of the list and also require constant space, or O(1). Importantly, the algorithm does not rely on any additional data structures or recursion, so the total space complexity remains O(1), making this solution highly efficient in terms of memory usage. To put this into perspective, let's compare our optimized approach with a brute force or naive solution. In a naive approach, we might create an entirely new linked list while inserting the value at the correct position. This would require O(n) additional space to store the new list, effectively doubling the memory usage. Moreover, the time complexity of the naive approach would also be O(n), because we still need to traverse the list to locate the insertion point. In contrast, our optimized solution performs the insertion in place, avoiding the overhead of duplicating the list and maintaining a space complexity of O(1). While the time complexity in the worst case remains O(n), the reduction in space usage makes the optimized approach significantly better. Finally, let's conclude with the mathematical reasoning behind the big O analysis. The traversal step is the dominant factor in the time complexity, as it grows linearly with the size of the list, making the overall time complexity O(n). On the other hand, the insertion step is a constant time operation, or O(1), and does not contribute to the asymptotic growth. When we combine these, the final time complexity of the algorithm is O(n). In terms of space complexity, since the algorithm only uses a constant amount of extra memory regardless of the size of the input, the space complexity is O(1). This balance of linear time and constant space efficiency highlights the practicality of the solution for this problem. One of the most common mistakes when working with sorted circular linked lists is failing to account for their circular nature. Unlike a standard singly linked list, the last node in a circular list connects back to the head. If you don't explicitly check for this circular property during traversal, you might either traverse indefinitely or miss critical insertion points. To avoid this, you should include a condition that detects when you've returned to the head node, signaling that you've completed a full loop. Another frequent oversight is neglecting edge cases, such as when the input list is empty. If the list has no nodes, your solution must create a new single-node circular linked list where the only node points back to itself. This ensures the circular property is maintained right from the start. Finally, inserting values that are either smaller than the smallest value or larger than the largest can be tricky. To handle this correctly, you can identify the transition point in the list where the current node's value is greater than the next node's value. This indicates the largest value, and any insertions at this boundary should appropriately wrap around the list to maintain sorted order. Another potential pitfall is encountering infinite loops during traversal. This often happens when searching for the correct insertion point but forgetting to terminate the loop. To prevent this, you need to ensure your loop either breaks upon identifying the insertion point or when you've returned to the starting node. Careful loop termination logic is essential here. There's also the risk of not updating pointers correctly when inserting a new node. Since we're working with a circular structure, any disruption to the next pointers of adjacent nodes can break the entire list. To avoid this, update the next pointer of the new node and the corresponding pointers of its adjacent nodes in a step-by-step and deliberate manner. This minimizes the risk of errors and ensures the circular property of the list remains intact. When it comes to interviews, circular linked lists are a great way to test your attention to detail and handling of edge cases. A key pattern to focus on is recognizing when traversal wraps back around to the head. This skill demonstrates a thorough understanding of circular structures. During the interview, make sure to communicate your approach for handling edge cases, such as an empty list or inserting values that are either the smallest or largest. This shows that you're thinking critically about all possible scenarios. While the insertion process typically involves a traversal and is therefore O(n), you can emphasize that once the correct position is found, the actual insertion is constant time. Be ready to discuss variations of the problem, such as handling doubly linked lists or converting between circular and standard lists. Additionally, interviewers might ask follow-up questions, like how to implement the solution recursively or extend it to handle doubly circular linked lists. Preparing for these extensions will leave a strong impression. Practicing related problems can significantly strengthen your understanding of circular linked lists and their variations. For instance, LeetCode 708 directly tests the concepts we've discussed here, such as inserting into a sorted circular list while maintaining its properties. Another relevant problem is LeetCode 61, which involves rotating a list and managing circular behavior, especially the wrapping around of nodes. LeetCode 206, which focuses on reversing a linked list, is excellent for sharpening your pointer manipulation skills. Finally, LeetCode 328 challenges you to rearrange a list into odd and even segments, which tests your ability to work with pointers while handling various edge cases. By practicing these related problems, you'll develop a deeper understanding and be better equipped to handle circular and non-circular linked list questions in interviews. There are alternative approaches to solving this problem, each with its own trade-offs. One option is to use recursion to find the correct insertion point. This can make the code look cleaner and more intuitive, but it comes at the cost of higher memory usage due to the recursive call stack, especially for large lists. Another option is the dummy node technique, where you introduce a temporary node to act as a placeholder. This simplifies handling edge cases, such as inserting a new head node, and makes the logic easier to debug. However, it does add slight overhead. Lastly, the two-pointer strategy involves using two pointers, one for the current node and another for the next node, during traversal. This reduces the risk of pointer mismanagement, which is particularly important in circular lists, but it can make the traversal logic slightly more complex. Each of these approaches has its strengths and weaknesses, so choose the one that best fits the problem's constraints and your coding style. Great job! Today, we explored how to insert a value into a sorted circular linked list, a problem that reinforces key linked list concepts. We discussed time and space complexities and highlighted the importance of edge case handling. Thanks for joining, and don't forget to like, comment, and subscribe for more coding solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!